In the 19th century, the rules of physics were built on a simple physical certainty. Waves need a material to travel through. Sound moves through air. Ripples move through water. Without a medium for the vibration, the wave simply cannot exist. Since light was known to be a wave, physicists deduced that the vacuum of space wasn't actually empty. It had to be filled with an invisible cosmic fluid, a luminiferous ether, that acted as the carrier for every ray of sunlight and starlight. This led to a logical consequence. As Earth orbits the Sun at 30 kilometers per second, it shouldn't just be sitting in this ether, it should be plowing through it. From our perspective on the surface, this motion would create a constant, invisible ether wind, blowing against the planet as we move through space. Detecting this wind wasn't a minor experiment. It was the most critical evidence required to anchor the foundations of classical physics and prove our understanding of the universe was complete. Albert Michelson realized he could measure this wind by splitting a light beam. If one beam traveled in the direction of Earth's motion, while another traveled sideways, the wind should affect them differently. The beam fighting the headwind should take slightly longer to return than the beam cutting across the current. The difficulty was the scale. The expected delay was so microscopic that no existing tool could possibly register it. To find a target that small, Michelson couldn't just use standard equipment. He had to build the most sensitive optical instrument ever conceived. At the heart of the experiment was the interferometer. A single light beam strikes a half-silvered mirror, which splits the light into two identical paths moving at a 90-degree angle from one another. These separate beams travel to the ends of the instrument, bounce off precision mirrors, and reflect back toward the center. When they recombine, they form a visible pattern of alternating bright and dark bands called interference fringes. If the ether wind delayed even one of those beams by a fraction of a second, the interference pattern would physically slide sideways across the detector. To eliminate any outside interference, Michelson and Edward Morley mounted the entire ton-heavy apparatus on a massive sandstone slab, floating it in a pool of liquid mercury to block out every earthly vibration. By isolating the instruments so completely, they had cornered the universe. Any movement of the ether would be undeniable. They pushed the floating slab to rotate it slowly, testing different orientations in space to ensure they caught the ether wind from every possible angle. Based on Earth's orbital speed, the math was clear. They expected a shift of roughly 0.4 fringes. But the detector showed almost nothing. The interference fringes barely moved. Thinking it was an error, they frantically repeated the test. They measured at noon and night. They waited months for the seasons to change, hoping Earth's changing position in its orbit would reveal the wind. But the results were always the same. Despite Earth moving through space at tens of thousands of kilometers per hour, the reading stayed stubbornly near zero. It wasn't a failure of the machine, it was a failure of the theory. The perfect physical measurement had proven that the luminiferous ether simply did not exist. The scientific community scrambled to save the idea, proposing increasingly desperate theories to explain why the ether was hiding. They were trapped by the math. Maxwell's equations had already proven that light is an electromagnetic wave that travels at one fixed, unyielding speed. A young Albert Einstein realized the only way forward was to accept the experiment's result as a new law of nature. He proposed that the speed of light isn't relative to a medium. It is a universal constant that is exactly the same for every observer, no matter how fast they are moving. Speed is simply distance divided by time. If the speed of light must stay the same for everyone, then distance and time are the only things left that can change. To keep that one number constant, space itself must contract, and time itself must slow down. The Michelson-Morley experiment didn't invent relativity, but it cleared the wreckage of the ether so that a new understanding of the universe could be built. Today, that same technology, the interferometer, is used on a massive scale to detect gravitational waves, measuring the literal stretching of spacetime caused by colliding black holes. It remains a testament to the fact that the most important moments in science aren't when we find what we expect, but when reality refuses to cooperate with our intuition. A moment of wonder. It forces us to look at light crossing the void and accept the impossible, that it travels across an absolute vacuum without needing anything underneath it at all.